Okay, so let's start. Okay, so I'm going to start with just a recap of last lecture and also the lecture before. Really just to kind of give you an idea of where you should be at in terms of what you understand. If you're not, then please make sure you go back and read. There's now 2 course note documents from the last 2 lectures. Please go back through those, watch the videos online, and basically try to understand firstly the interpolation functions. They're important to understand the kind of just the basic mathematics of those. Essentially just linear shape functions that we're deriving. We're showing the differentiation of those, the integration of those. They're essentially the key mathematical skills for what we're trying to do. And then I went through the various steps in an example solution. Now, the one we saw last week was the second derivative is equal to 0 last week. Now, this week we've actually got a right-hand side, a forcing term, which makes it slightly more complicated, but it means we can go back over the derivation, and it's almost exactly the same process. And if you remember from last week, there were some fairly strange steps, things like integration by parts, and inserting the functions, which I'll try to explain in more detail. But again, please shout out if it's not clear. Then I'm going to talk more about boundary conditions. So you'll notice the note at the end of it basically just mentions the boundary conditions, and then the matrix gets smaller. And I'll explain in more detail how we start to apply boundary conditions, various types of boundary conditions, and this becomes important for when we start talking about industrial applications. The only thing that's different in any CFD or FEA simulation is basically the boundary conditions. So everything else, you're solving the same set of equations. Your boundary conditions entirely dictate what solution you're going to get. So they're probably the most important thing to understand. And I'll explain it just in a kind of equation sense here, and then later on we'll talk about how we kind of apply them in more general cases. I'm also going to start trying to introduce some Matlab code. I'll start doing that gently at first. I'm aware you had the training course on Matlab, which was like 4 sessions at the beginning, and then I guess nothing since then. So you just had all of that. Okay, so what I'll do is this week I'll try to include bits and pieces of Matlab, and then next week we'll include even more, and then after that we actually start on the applied exercises where you have a chance to start doing things with Matlab. But what I'm going to try and do more and more is just incorporate bits of Matlab to show you how you solve essentially the equations we're talking about. And then towards the end of this lecture, depending on time, I'm going to go through an example solution of a more complex differential equation. And again, this is just part of this idea of moving to more complex systems so that you're getting to the point where you're able to solve the example we talked about for the assessment exercise. So we're week 4 now, lecture 3, and next week, same again, it's week 6 where we start to have the lab in the morning at 1:38. So as always, the QR code's there. Thank you very much for anyone who filled this in last week. Please continue to do so. And essentially, you can, what I'll do is I'll keep this open from the previous QR code for the week. So please feel free after the lecture, if you've got any comments that kind of stay with you, please feel free to use them during the week. And as I say, don't worry about registering when you make comments. The idea is you register just once for that and then make comments anonymously and say whatever you want to say, and that feeds into the course. So there was some positive feedback. There was also some constructive criticism, which was good. So people generally wanted a bit more explanation on calculations, which I assume is the kind of matrix bit at the end, but probably in general just more detail, and that's fully understandable. We covered a lot very quickly towards the end of last lecture, so the idea is we're going to keep going back over that to kind of reinforce. Just to reassure you, that derivation at the end was essentially pretty much, okay, it's the simplest example, but that is the full process of the finite element analysis derivation. So understanding these interpolation functions is kind of key to the process. Everything else we do from here is just more complicated. So if you can understand these basic fundamentals, then you have the kind of key skills. So don't worry if you felt it was a bit difficult or a bit too much in that last lecture, but we'll keep covering it. People ask me to engage more and try not to read so much of the slides. I say reading off the slide. Apologies for that, it's quite difficult because I'm kind of trying to write on that and read it at the same time, but I'll do my best to do that. But you can help me out by shouting out. If I'm not engaging, I'm going too fast, I've done something, especially if I've made a mistake, shout out. Feel free to interrupt me and ask questions if something's not clear. And I'll define the equations for that. So, and again, keep the feedback coming. So anything you don't like and anything you do like, that's appreciated as well. So just please keep feeding back on that, and also the traditional way, shout out. Okay, so recap of last lecture, 1D solutions to equations, and we'll talk again about the key steps. So for me in this presentation, what's important is to distinguish kind of the key conceptual steps and then what is just mathematics. And I think by being clear about that, the bits of mathematics you just have to work through and doing yourself and convince yourself work. The key conceptual bits are the ones that are difficult. They're the bits that you wouldn't think of yourself. These are the things that have come from years of research in this subject. I'll try to explain why we do that. The reality is you can do it different ways. You'll probably get less good answers. And I'll talk a bit about why that is. But the reason for showing these kind of steps and emphasising them is because they're the ones that maybe are counterintuitive and things you wouldn't think to do yourself when working through this problem. And then I'll start to incorporate a bit of Matlab code for the 1D case. Talk about grids, we'll talk about boundary conditions. Numerical stability I don't think we're going to get to today, just because these equations are actually fairly stable, and also because I think we'll wait till we get to the next lecture and we'll have a bit more Matlab code before we talk about that. Okay, so you've seen this slide plenty of times. Hopefully it's at least kind of frames the problem in that, this idea of mathematics is the idea of defining functions. These functions, we can then define derivatives. And this is the whole point of the continuum hypothesis. This is why this is a branch of continuum mechanics. These kind of phrases you hear bandied around. But the key point here is that essentially, we're defining some sort of derivative using the calculus. And this is basically this limiting case as you zoom in on this point on the line until you've got this kind of gradient operator that gives you an approximation for the gradient at that point, the derivative at that point. And in doing that, we then end up with useful equations for solving physics. So these are differential equations. So the simplest example of this is kind of linear first order differential equations of the sort we have here. And then just slightly more complex is second order differential equations. And so do you remember I talked about terminology? First order is just the highest derivative. Second order is because you have a second derivative, and so on. In this course, we'll only get to second order differential equations. Generally in physics, the actual equations you see don't really go above second order. There are some that have kind of slightly higher order, but generally most things are only second order. So if you can solve that, you can solve most of the problems of interest. And then I mentioned nonlinearity, and that's when you have a function times the function itself, and that's when they start getting more tricky. We're not going to cover those in this course, but again, feel free to read around, ask questions if you want to know more about that. Okay, so in the simplest possible case, we can just solve these directly. In this case, we're just basically integrating both sides just to give us a function and then some arbitrary constant of integration. For a second order differential equation, we have to integrate twice. We end up with two arbitrary coefficients. And these coefficients are basically what we need boundary conditions to specify. And I try to link that back to this concept of boundary conditions and how they're useful. 1 second. Perfect. So I'm just making sure it's actually recording. Okay, so then in terms of the solution to a differential equation, the way to think of these is we solve these differential equation and we get functions. So the functions in this case here, the first derivative gives us this first coefficient, second derivative, second coefficient, and then we end up with here what is essentially a polynomial. So that's x squared, which is the kind of parabolic equation here, plus these extra two terms. So this is a really, really simple example, and just to give you this idea, we have these differential equations and they do have exact solutions in some very rare cases, but really the number of equations we can actually solve is a very, very small set of the full equations that are possible. So often the functions we're talking about are so complex we can't solve them exactly. The solution probably doesn't even exist. You get all these kind of complex chaotic behaviour that the butterfly effect is based on, and all of this kind of essentially unsolvable kind of equations come from these differential equations. So the point here is that what we're going to do with FEA and numerical modelling in general is to basically approximate these functions, and that's using essentially linear shape functions. So just to recap of kind of the overall physics picture, and I've now got under braces to kind of highlight the various terms. So this is just a form of Newton's law. So if you work in solid mechanics, this is basically the equation you're working with. This is just F equals ma essentially. So on the left we've got our mass or density in a solid because it's a block of substance that has a density rather than a mass per unit volume. And then the acceleration of that substance is equal to the divergence of stress. So you can think of this as a kind of force term, but stress in a substance is quite a common engineering concept, and it's a useful idealization. If you slice through, you get a state of stress. the divergence of that stress will give you the forces on that. And then we have these body forces. These are things like gravity or things that are applied from outside the system. So in the car example, that would be the wall, would probably be a body force. So in this, the examples I gave you, this was just a stretched element. This was a fan blade failing, and then the car crashing into a wall. And these would all be examples where you would use Newton's law, but in this kind of continuum form. So for fluid mechanics, this is again Newton's law, but in a slightly different form of what's called the Navier-Stokes equation. On the left-hand side, we have the essentially the acceleration. So this is mass times acceleration again, split into a different reference frame where you sit and watch fluid flow past the point. So we have the change of fluid flow inside the volume, and then this nonlinear convection, and this causes all of the kind of turbulent-like behaviour that you typically see. You have a pressure-driven term, which is just a pumping force, or in weather prediction, that's where you see the high pressure and low pressure, and that drives wind between the 2 points. And then diffusion is just the kind of spreading of a droplet. And it's this diffusion term here that we're actually going to solve in lots of the examples, and then start to include more physics. So this is an example of turbulence. We have this is actually a solid and liquid interface, but a turbine with the fluid flowing past that, and then this is an example of boiling with liquid vapor, I showed. We're not going to talk more about Maxwell's equations. I've personally never used them, but they're essential if you're working with electromagnetics, radio wave transmission, electric motors. And you can see these are essentially differential equations. You've got the added complexity of a curl term, but these are actually linear equations and possible to solve using exactly the same techniques we talk about here. And the electric motor example is quite nice because you can actually combine thermal fluid models and cooling. Yes, together in one single model. So, and then this final example is just basically conservation of energy. So this is just a model for flow of energy, and again it's of the same form. We have the unsteady change in energy inside. So this is the time change in energy inside a box, and then that's equal to the energy that flows out of the box due to flowing fluid. The work done on the fluid. So in a thermodynamic sense, that's PdV, or just the kind of stretching effect of the fluid. And then this heat flux term that we talked about being essentially what's used in Fourier's law, just flow of heat or conduction. And then finally we get to the equation we're going to solve in the exercise. And this really is just the kind of equation that incorporates lots of these elements that we've talked about here, and just allows you enough complexity that you can start to get a feel for how these work. So we have a kind of diffusion in X term, diffusion in Y. We have a U-dependent term, which I'll talk about towards the end of this lecture, and then this kind of forcing term here. And again, we can solve that. It's a two-dimensional equation, this example. Okay, so coming back to this definition of a derivative, FEA, essentially we approximate that derivative as a series of straight lines, and that's the process of finite element analysis. So in this particular example, we're going to just go back to this terminology where we have the concept of a function, which is some unknown function. And as I said, this is so complex, generally we can't possibly describe it exactly. So we approximate it as a series of straight lines. The key point is these straight lines meet and they're continuous or joined at the nodes between them. And then essentially we're fitting them to the function as closely as possible. And we'll come back to that with the weighted residual idea. So just the terminology again, U1 is essentially just saying U at the value of X is equal to X1. Where X1 is just the point on the X-axis. And then these are nodes, the points where they're connected, and then they're elements, and they each are numbered with element numbers. Okay, so the first task we talked about in the first lecture was to define a straight line, or an element which joins the 2 points U1 and U2 together. And the process we did for this was basically to define an equation for straight line, mx plus c, use the fact that we know the value at both ends, u1 and u2, and x1 and x2, and define this element equation that's essentially of the form n1 as a function of x times u1, which is the constant at this point, and n2, which is a function of x, and the constant at u2. So does that make sense? Everyone remembers me doing this? Everyone's happy with that? So this is really what we're going to build on today. Is there any element of this you want me to go through? So does anyone want me to go through this first linear function again, derivation of that? Are you all happy with that? So put your hand up if you want me to do that. Okay, so we're at least happy with that. And then the derivative's fairly straightforward, is that okay? So the key point here is what we've done is derive this linear shape function where all of the x dependence is in n1 and n2. So the derivative of this just becomes the derivative of these two shape functions. And then the integral we only covered briefly. Does anyone want me to kind of talk through that again? Okay, so there are notes for all of this. Feel free to go back to them. But I mean, if you remember before I went through this process, it's just mathematics. There's nothing conceptually difficult in this. Really, just it's a bit odd that you arrange it in this particular form, but you end up with just an expression for n1 and n2 like this. Derivatives, if you remember, give us minus 1 over h and 1 over h, and then we end up with this expression for the element, which is u2 minus u1 over h. So it's essentially the definition of an approximation for that derivative. And then the integration proceeds basically by integrating the element. We take the integral of each of the individual shape functions, and then this was a process that was a little bit tedious, but we just go through, integrate each of the expressions, collect them together, use this expression for the product of x2 minus x1 all squared, and then we end up getting something which is basically just h over 2. So again, there's notes on all of this if you go back, but the key point is we end up with this expression. It's essentially the trapezium rule. That's basically the integration of these elements is half x2 minus x1 times u2 plus u1. And this isn't really surprising because essentially the trapezium rule does exactly that. It approximates a function as a series of straight lines, and then underneath each of them is a trapezium. So it's all wonderfully consistent. Okay, so I talked slightly about the kind of more general notation. So this idea that you can actually define this superscript element e, which we can put as a number. So for example, ne, and then the next node will be e plus 1. So just to show you how that works in practice. So if we put in the value of e is equal to 1 on this, we end up with t1 is equal to n1 t1 plus n2 t2. If we put in e2, we get t2 is equal to n2 t2 plus n3 t3. So the reason I mention this is because when we come to look at Matlab, this is essentially a way of writing very, very general descriptions. So in Matlab, you define a number of elements, which can be 3 initially, but then we can make any arbitrary number. And this is the key point. We're going to start writing things in more general ways that allows us then to write equations for any number of elements. And we can basically make our approximation as detailed as we want, as detailed as the computer allows us. So one key point that comes from this is the number of elements is one more than the number of, the number of nodes is one more than the number of elements. So if this is 3, then this just becomes 3 plus 1. And then what we do is we actually run a loop over the different elements, and then for each of the elements we'd loop over the nodes. So this is a nested loop. So basically this from the survey is one of the areas where I think people were possibly slightly weaker on in terms of their background, and that's fine. I think it's one of those things, you've either done programming or you haven't. If you haven't, then just please feel free to ask if you've got questions on this. I've got office hours after this lecture from 4 till 5 if you have questions on the Matlab, or again on Wednesday. So people say they had no experience of loops and branches, which is quite interesting because then people have said they've used Matlab for solving mathematics. So I think maybe people were possibly thrown by branches. I mean, this is basically just an if statement, so a logical branch. Maybe slightly non-standard terminology, but you'd say something like if x is equal to 1, for example, do something else. If x is equal to 2, do something else. So that's branches, and then the looping is what we've just seen for the 4 statements. So again, I'll do my best to kind of try and at least cover these from a level of people who haven't seen anything at all on this. I'll do my best, but I think the problem is with the difference in backgrounds, you're going to have to probably go away and just read up if there are things on Matlab that you don't follow. But there's good information online. So just to kind of, with that in mind, I just want to kind of really set out exactly what we're saying here. So bear in mind, in computer programs, you're not equating strictly in the mathematical sense. It's a definition. So what's on the left is defined to be what's on the right here. So n elements is defined to be 3, and then n nodes is equal to n elements plus 1. So n nodes will be 4, for example. But what this means is you can do some strange things, like you can say n is equal to 3, and you can do n is equal to n plus 1, for example. Mathematically, that would make no sense. That would give you 1 equals 0. But in computing, what you're saying is what's on the left is defined to be what's on the right, and you update that value on the left. So just bear that in mind if you're a little bit, if you're new to programming. And then the loop here, essentially that loop, the way Matlab works is a statement of the form 1 colon elements essentially creates a matrix, which would have 1, 2, 3, ... to n elements. And this for statement says just go systematically through those and keep updating E each time. So each time E has a new value. And then what we're doing with this inner loop is we're using, the element number, and we're going from that element number, which would be, let's say it's 3, it'd be from 3 till 3 plus 1, which is 4. So it's exactly what we saw when we wrote the equation for the straight line. Remember we had UE is equal to n at E and n at E plus 1. So it's just computationally the same thing we've got at the bottom there. Okay, so just to get you to do something, we're actually going to take this equation, and it's exactly the same as the one last week, but we now have a forcing term on the right hand side. So you've got about 10 minutes now if you just want to solve this equation analytically, and then use the boundary conditions we have on the right hand side. And the boundary conditions, we have here, the boundary conditions this time essentially are that it's 0 at both ends. So whereas before we actually had t was not equal to 0 on one end, this time we're going to do that. By the way, if this seems really obvious, feel free to start thinking then about how we're going to do this with finite element analysis. And any questions, please stick your hand up.
The second t value, is that meant to be different values to t equals 0?
No, it should be t. No, it should be 0 at both ends. So essentially, we've got a boundary condition at 0 at both ends.
Okay.
Yeah, if we'd done that before with it equal to 0, we'd just get a flat line. It'd be a boring solution. But in this case, because we've actually got a forcing,
Okay.
we get something different. But okay, and then we basically now need to stick in the boundary conditions. So the boundary conditions we know are at t of x is equal to 0, so we can put that in first of all. So we put in just the values of x is equal to 0 here, so we end up with basically just equal to c2. So we know c2 is equal to 0 for that particular case. And then for our second boundary condition at c of x is equal to 0.3, we know that's also equal to 0. So what that gives us is f times 0.3 squared over 2 plus c1 times 0.3. Okay, and then we can basically just rearrange in order to get c1. So c1 is just going to be equal to, we can actually cancel 0.3 on both sides of the equation just for simplicity. So c1 is going to be equal to minus 0.15 f. Sorry, let's make it around this. So 0.15 f. So we just basically cancel 0.3 on both sides and then rearranged, moved f to the other side, and we've divided 0.3 by 2. So we substitute both of those into the original equation. So t as a function of x is equal to f x squared over 2 minus 0.15x. Okay, does that make sense? Everyone happy with that? Anyone completely disagree or see any mistakes? Okay, so to give you some context for this, so this is essentially a solution of a reduced solution of various forms of the equation, but probably one of the most physically intuitive is of the Navier-Stokes equation. So if we have an example where we have no evolution in time and no convection, so that's essentially a system where you're at steady state and there's no turbulence, there's no high Reynolds number flow, then what we end up with is pressure-driven flow. So you can think of the pressure gradient as being like a force, and this right-hand side is essentially just a diffusion term, which in our particular case is just d2u by dx squared. So the solution we've just derived, if we go back, is actually parabolic. So it's x squared. So you can think of it as a parabola. And in fluid dynamics, that's essentially channel flow. So you can imagine if you've got a pipe where you have a fluid being pumped, either by gravity or by a pressure gradient, and these are the walls, the actual flow would form this kind of parabolic profile. And you should have seen this in kind of fluid dynamics courses. So this is essentially a solution to the right-hand side of the Navier-Stokes equation. Similarly for stress, if you consider, say, an example where you've got some bar, for example, that's kind of fixed to two kind of constant temperature walls, and you're heating homogeneously underneath it, you can imagine you'd actually see a kind of temperature profile that would essentially be parabolic across that. Or similarly, if you're looking at a fluid and you have shearing within that fluid, so this kind of stress term where the fluid is kind of stretched by the action of the fluid shear, what you can see within that is that we heat up inside the channel, and again you would get basically heating in the center of the channel and constant boundary conditions at the wall. So you'd end up with this kind of temperature profile due to heating. So, again, this is kind of physically one of those cases where for the case of no advection and no unsteady term, we get some of the equations, some of the terms in these equations. And again, we're building up in complexity. So we've now got an extra term in the equations of motion. And then finally, you can see for this equation, it's essentially just, if you ignore these two terms, we have basically now this extra forcing term. So we're moving towards the example we'll eventually have to solve step by step. And that's just a derivation now. Okay, so the next step is to solve this using finite element analysis. So we're starting with that particular equation, and we're just saying, as we've done before, we're going to write it in the form AU minus F, where A is just simply this operator. So you can see essentially, in this particular example, A of t is equal to F is of that form, where A is just d2 by dx squared of t is equal to F. So this is just A there. So you can see hopefully that it's of that form. And then the idea of the finite element method is to approximate this using a sum of piecewise elements, if you like. So this kind of solution that we have, which is the AU minus F, is replaced by this AU element minus F, where the elements are the individual straight lines that are approximating our function. And so the aim of the finite element method is to basically do a least squares fit, to reduce the kind of linear approximation to be as close as possible to the true solution of those equations. And in the limit that we had an infinite number of straight lines, we would get the exact solution to those equations. But in practice, we can only ever get an approximation for that. Okay, so the idea now for this section is basically to reproduce what we did last week. So with this equation, we're going to basically write both sides in terms of the weighting function. And then the key steps were use integration by parts to express the right-hand side as basically two expressions that are first-order derivatives. Now, so your first exercise is to actually try doing this. We talked about it last week. It's also in the notes if you want to check, but really just to work through yourself using the integration by parts and just reassure you how we do that left-hand side. It's just pure mathematics. Also consider what happens if you actually try taking this expression here for, say, an elemental shape function, and take the second derivative of that. If you take that second derivative, see what would happen if you didn't do integration by parts and you actually tried to solve that directly. The next part is to actually take this integration by parts expression and substitute in the expression for t and w as linear approximations, and then the next step we'll collect them together and solve for each node as a matrix. So I'll give you maybe just 5 to 10 minutes just to have a go at the integration by parts on this left-hand side. Does that make sense? Is that clear? So basically, so what I'm saying is take this by dx squared dx and use integration by parts to rewrite it as d omega dx dt dx plus a surface term. So when we come to the assessed exercise, this is one of the kind of steps that you'll have to be able to show in the derivation. So it's useful to understand now. And like I said, the other thing to think about is why we do this, why we actually need to do integration by parts, why we can't just solve it directly using these linear shape functions. Any questions on this, by the way? Anyone completely lost? Or you stick your hand up, I can come around, by the way. You don't have to shout out. Even if you're just completely no idea what you're supposed to be doing, please. Okay, let's move on. Anyone got any questions? Is that okay? Makes sense? Okay, so anyone got an idea why we do that? The advantage of doing integration by parts here. Any thoughts? So I mean, one of the things to consider is if we took the equation for an element, which we have as nx t1, n1, plus n2 x t2. If we take the first derivative of that, dx, if you remember before, we actually end up with basically dn1 by dx t1 plus dn2 by dx t2. And that then ends up being basically t2 minus t1 over h. So each of these basically become 1 over h, and this becomes minus 1 over h. So we end up with just constant expressions. Now if we took the derivative of this expression here again, so we were going to take d2t of the element by dx squared, we end up with 0. So actually by using a linear shape function and trying to do a second derivative here, you actually end up with a problem, and you can't actually use these linear shape functions. So this trick here is actually a way of getting essentially using linear shape functions for what is a second order function. So it actually allows you to kind of get higher order accuracy with lower order functions. So you're actually guaranteeing continuity of gradients. Now another way to think of this is, if you actually look at the way the derivation works, and I'll come back to this in a sec, is we actually end up with this surface term here. And we end up with this internal term. Now, as I'll show you later on, now this is the function here is for a single element. So if you think about what we're actually doing here, this is between t1 and t2. So we're actually deriving the equation for a single element. And then we do this exactly the same process again for t2 and t3. But for this particular element, the actual surface term between the two of them, we're actually showing that these terms cancel at that surface. So in doing that, we can actually express it as a surface term and an internal term, and the surface terms cancel, which means that we don't actually have to worry about those terms, and we end up actually just having to worry about the internal terms. Now, I'll come back to that in a sec, show you mathematically, and then we'll come back to it in a sec and see why that happens. But I just want to show you again what we did last week, just to kind of reiterate the process. So we've done this integration by parts on this expression here. And then the idea here is we're actually going to replace both these internal derivatives with the derivatives of shape functions. So as we've already said, dt by dx is just t2 minus t1 over h, and d omega by dx is just omega 2 minus omega 1 over h. So these are just the consequence of the derivatives of a linear shape function. They're just constants that are the difference between the two ends. So we can basically just substitute those into our expression for the internal. So let's call this internal I. We'll just say I here is basically minus, let's leave it plus, the integral between x1, x2. So we basically just got omega 2 over h times t2 minus t1 over h dx. So what's nice about that is that we essentially have no x dependence at all inside here, so we can actually just integrate this directly, and what we end up with is basically x2 minus x1 over h squared is equal to omega 2 minus omega 1 t2 minus t1. Now, by definition, x2 minus x1 is just h. So this is basically h on top and h on the bottom. So we can cancel this and this. So we end up with just an expression that's 1 over h, omega 2 minus omega 1, t2 minus t1. Okay, now if you remember the surface terms, we'll just call this S. The surface terms essentially are just putting in the limits. So we just have omega times dt dx. And all we have to do here is just stick in the limits of x1 and x2. So we're just going to write that in notation as omega 2 times dt dx evaluated at x2. So that line down there basically says just the derivative evaluated at that point in space. Minus the upper limit, which is omega 1 dt dx1 at x1. Okay, does that make sense? Everyone happy with that? So we're just sticking in the limits there for the surface term. Okay, and then the last part of this is to basically collect together the terms in terms of omega 2 and omega 1. So if we write out the whole expression of I plus S, it's minus I plus S, just based on my convention from before here, we're going to end up with minus 1 over h, omega 2 minus omega 1, t2 minus t1, plus omega 2 dt dx at x1 minus omega 1 at dt dx, sorry that should be a 1 there, at x1, and then we're just going to collect together, and this is all equal to the right hand side. We'll come back to that in a sec, but so that's going to be equal, then we're going to collect together the various terms. So if we collect together terms in omega 1, that basically gives us the expression so t2 minus t1, 1 over h times t2 minus t1 minus dt dx at x1 plus the term for omega 2. That's 1 over h, t2 minus t1, it should be minus here, plus dt dx at x2. Is that okay if I made a mistake? So the key point here is we've collected together the terms in omega 1 and omega 2. Now the reason we do this is omega 1 and 2 are arbitrary weighting functions. So what this means is inside these brackets we have these individual equations that are valid by themselves, and I'll come back to that and show you in the slides. The last thing I want to show you just very briefly is this new right hand side term, which if you recall is basically x1, x2, f omega dx. Now one thing I want you to notice from this is that this entire left hand side is exactly what you've seen before. So the process of doing the right hand side is basically one of just dealing with an extra term. So everything you've seen so far, when I show you these equations, they're made of different individual terms. You can just treat each of them individually, and there's kind of tricks to each of them, but you know the reality is as you build up a kind of understanding of the various terms, it means you can then solve kind of more complex equations. Now the integral of this term here, let me just get some more space. Essentially what we're doing is just the integral of a constant which we can move outside. So we move f outside, so it's just the integral of this weighting function dx, which is just the integral of n1 omega 1 plus n2 omega 2 dx and x2, and so that's just going to be equal to omega 1 f times the integral of n1 dx plus f omega 2 integral of n2 dx. So what you can see is this is exactly the same form as the trapezium rule that we saw earlier on. And so what you're going to end up with is exactly the expression for the trapezium rule, which is just going to be equal to f brackets omega 1 over 2 times h plus omega 2 over 2 times h. And so from now on we're just going to define that as f. But essentially what this means is we end up is collecting these terms together is you have just fh over 2 times omega 1 plus omega 2. So the entire contribution of this forcing term is just fh over 2, which is going to appear on the right hand side of our equations and in our matrices. Okay. Okay, is that okay? Does anyone have any questions on that? Seem okay? So I'm going to just show you a couple more things and then we'll have a quick break. So I just want to show you how that then gets collected together for the various equations. Now, the thing to remember here is that we've actually, this equation, this derivation was for a single element, so a single piece of a kind of global system. So we did the process of integration by parts. That was rewriting the left-hand side as two first derivatives. We then replaced both of those derivatives with the expression for the linear approximations, and in our case we did the derivative of those linear approximations. For the right-hand side, we essentially just integrated that expression just over f dx, and that is exactly the same as the trapezium rule. So just go back to that if you're not convinced, but it is just purely mathematics and gives you essentially this expression of fh over 2, which we're just going to define to be big F from now on. And then the final piece is collecting together each of these individual equations for each of the elements and putting them together as a single matrix. So I wanted to show you this visually, and hopefully this addresses at least some of the concerns. So the endpoint we got to just now was one of essentially these two separate equations, each of which is multiplied by this arbitrary constant. And then on the right hand side you can see also multiplied by omega 1 and omega 2. So the trick we did is to collect these two together as two independent simultaneous equations. So the way to understand that is this equation is satisfied provided each of these terms is satisfied. Now you can actually, one way this could be satisfied, because omega 1 and omega 2 have to be constant, they have to be non-zero by construction. The only things that can be zero or can basically balance in this equation are the things inside the brackets. So essentially what we do is we collect together the expressions on omega 1, and that has to be true for omega 1. The expression for omega 2 has to be true, and we have two simultaneous equations that if we solve together will give us basically a satisfaction of the original equation. Now the way we solve simultaneous equations, as we saw last lecture, is basically to put them in a matrix and solve them. So what we did here is we collect together the coefficients of T1 and T2, and on the right we have together the new forcing term and these flux terms on the right hand side. So essentially we're just forming a matrix of these simultaneous equations. So let's start with the left hand side. So the way to understand this here for the system of equations is essentially, you know, this is the integral here between x1 and x2 of d2t by dx squared. This is the integral here between x2 and x3 of d2t by dx squared. And this is the integral between x3 and x4. So essentially what you find is that because they're using the same linear shape function, the actual coefficients are the same in all three cases. So we get exactly the same there. It's just the values at the nodes are different each time. So essentially this is just the process of collecting the same expression for each of these linear shape functions. Somehow managed to exit. And then essentially what we do is we basically pad out. So if you imagine for a single element, the actual bit that we just saw was actually just for this element, and that would be, so the process of matrix multiplication, you multiply this by this. We'd multiply, okay, not red, multiply say this term by this term. We'd then multiply this term by this term, and so on. So we can actually take our local expressions for each of the individual elements, and we can just stick in loads of zeros. And this matrix is exactly the same as the one you saw on the previous slide. The only difference is we just got lots of zeros, and they're multiplied by each of these coefficients, and they end up being 0. So essentially we have, this is exactly the same for that function. We do the same thing here for T2 and T3, and again it's exactly the same function. We just pad out a load of zeros, where, you know, this expression here would be multiplied by this expression. This would be multiplied by this one. And then say the 0 here would be multiplied by that. So it again contributes in no way. Does that make sense? So essentially by padding out by zeros, we've done nothing other than just get our matrices to be what we call global matrices. And then we add all of those together. So in adding them together, what we have is assembled a system of simultaneous equations for all of the nodes in our system. And then by solving that system of simultaneous equations for all nodes, we get an overall solution that satisfies the equation for the entire system. So that's the process of building it for the individual parts, and then sticking it together in a kind of overall matrix. So now just consider the right-hand side. We do exactly the same thing on the right-hand side. What we're doing here is we're adding the forces. Now bear in mind this is an external body force. It's a force applied to the entire system. So you can think of it like gravity. Now gravity if you think of gravity on a truss, for example, on a car, it'd be applied the same to every single bolt on that truss. Physically you can think of it exactly the same thing. There'd be a force of gravity here, there'd be the same as the one here, the same as the one here. Mathematically that's what this says. It's basically we just have the same expression on each of them, and you add them all together and you get an expression for the overall expression for the forces. The overall forces acting on a truss. And then you've got this convention of half between those. And then the final term is these fluxes. Now the fluxes you can think of as being gradients in temperature as being heat flux. Now if you've got the value of temperature T1 and T2, now you imagine heat will flow from hot temperatures to lower temperatures. So T2 is higher than T1. So what we'd expect is that heat would flow from hot temperatures to cold temperatures. And this gradient in temperature you can think of being a flux, basically flow of energy. So what we have essentially is this kind of picture of flowing energy throughout the system. So the derivative of temperature is the heat flux. And this heat flux we have at each of the individual nodes. So as we said before, these expressions at x1 and x2, these surface terms as I called them, are the surface terms here and here, for example. And these essentially would be exactly the same as this surface term here. And so what we see is that the values of fluxes at the nodes cancel out. And this is this idea of taking this integration by parts to split it into two first derivatives and then the surface terms that then actually cancel between the two nodes. So physically what we're left with for the entire system is just two values of flux just at the two ends. Now physically this makes sense. Our system internally is entirely self-defined by the interaction of the elements and the fact they're joined together. The entire dynamics of the system is specified by what happens at the edges, what happens at the boundaries. And physically this makes sense. If you had a beam and you were heating it from two ends, what happens inside is entirely determined by those two end conditions. So I think probably time for a break now, because you've had enough of me talking. Let's take 10 minutes for a break, but essentially this leads into the idea of boundary conditions, and I'll talk about that afterwards. And any questions, feel free to come down and ask me, or get up, walk around, take 10 minutes. Okay, to make it clearer, less clear, just maybe. Oh, so the table on that. Yeah, okay, fine. So, in terms of the numbering of the elements, and this in one dimension it's fairly trivial because numbering will always be 1, 2, 3, 4 in the global coordinates. It's not too important. You have local numbering. It's a bit like postcodes, for example. Postcodes, or I don't know, street addresses. Within the street, that number makes sense. But the next street of that number applies to the house. Yeah, so okay, so broadly speaking, boundary conditions are classified either as Dirichlet or Neumann boundary conditions. So Dirichlet specifies the variable. So for the case of Newton's law, for solid body mechanics, that's the displacement. You can think of a beam, that's how much it varies. In fluid dynamics, for the Navier-Stokes equation, it's the flow velocity. You can imagine this being no slip at the wall or fluid inlet. And then for the thermal case that we'll be talking about, that's just simply temperature, specified directly. And then we've got the Neumann boundary conditions, which specify the derivative of the variable. So that's strain rate, for example. So strain, for example, in solid mechanics, so the derivative of the displacement. For flow velocity, that's strain rate. And for heat flux, that's essentially the flow of heat. And this potentially would be closer to, say, the experimental reality. You may be controlling the strain in your experiment, and you want to be able to do the same thing in your numerics. Or you have a known heat flux from, say, a heater. And physically you want your model to match that. So the first thing to notice about the equations that we ended up with as a result of this process. So On the left-hand side, we've got our matrix of coefficients for the entire system. This has 4 elements. On the right-hand side, we have our forcing term. So this is just a force applied at each point. And then we have these two end boundary conditions. So the boundary conditions are basically here and here. And these boundary conditions, you can see, are in the form of fluxes. They are Neumann conditions. So these are called natural boundary conditions, and the ones that occur naturally as part of the finite element process. Now, typically, we actually want to enforce Differential, or what are called essential boundary conditions. So there's a bit of a trick to this. The simplest way to think of this is if we're enforcing a zero boundary condition. So imagine we've got a situation where we know that T1 is going to be equal to 0. Now, you think about what happens with our matrix. In our matrix, we always multiply basically across the columns and down the rows. So this first term would always be multiplying T1. In this case, this first term will be multiplying T1, and so on. So if we know that T1 is always going to be equal to 0, one option is basically just to enforce that by setting this entire row to be equal to 0. Now our matrix has to be square, so we can actually then essentially set the corresponding top row to be equal to 0. Similarly, if we wanted to set the bottom boundary condition, now bear in mind the example we had before where t is equal to 0 at the other end is the same process. So in this case, the terms that multiply t4 are this term, this term, this term, and this term. So essentially we're setting that entire row, this column into 0, and we then set the corresponding row to 0. So in doing that, we can essentially reduce our equation down to equation where we fix the boundary conditions for that. And then this can be solved directly. So for example, we have here where we have essentially 3 elements. We have a domain that's 0.3 meters. Each of the elements individually is 0.1. It's the entire domain divided by the number of elements, which is just 3. And we're saying for a case where we have force is equal to 0.1, that's F. It's just 1 times 0.1 here. So we end up with basically a system of equations that we can solve. So you could either solve them as simultaneous equations. So, essentially if we had these two simultaneous equations here, we can just solve them in a normal way, or we can stick them into Matlab as a matrix. And if you remember before, we talked about this, where this matrix is K, this matrix was T, and this was F. We can basically rewrite this using K to the minus 1 of F will give us the matrix T. So we can essentially solve this by just inverting the matrix and multiplying the right-hand side, and that will give us expressions for T2 and T3. But this process is identical to solving them as a set of simultaneous equations for our system. Does that make sense? Is everyone happy with that? So just to give you an idea of how this works in Matlab, I've got Matlab code that does this. Now this is all on the blackboard, so I encourage you, even if you're not familiar with Matlab, to go through this, work through each of the steps and just understand. And for me, the best way to learn how code works is just to change things and see what happens when you break it. So play around with this, but this is basically in code exactly what I've just said. Number of elements we set to 3, and then with the number of nodes is plus 1. So getting h is just basically the main size, which we call L, 0.3 divided by 3, the number of elements. What we do is we set our K matrix up, so this is basically just defining here, it's just defining this matrix here. What's nice is because we've actually defined h as a variable, we can actually write it almost identically to the form we have here. This semicolon just says we want to have a new row. And then our right hand side here you can see here is exactly the same as that on there. And then the actual solution process you can see is actually, in terms of Matlab, made almost exactly the same as we do this in terms of solving it. So we basically just have k to the minus 1 of f, where this is f, this is k, this is t. And we can actually get t by just doing this process here. And then essentially what we're going to do is we're going to plot the solution here. And I've just defined an array x nodes, which is just at 0, h, 2 times h, and 3 times h, which is the location of the individual nodes. And we're going to plot those nodes against the solution to t here. And then we've also had to specify basically the 2 boundary conditions at the 2 ends. So bear in mind, this array here will give us T2 and T3. We also have to then add in 0 and 0 because we've specified known boundary conditions of 0. And then what I'm doing is I'm actually deriving what's called a linear space. So this just gives you 100 values between 0 and L, and using that to plot it against the analytical solution. So the solution you got from solving the equation directly, which was just the parabolic we have here, as 0.5 times f times basically x squared minus L times x, which is basically the form of the solution to the equation exactly. So just to convince you, this gives you the same thing. So the parabolic is the exact solution, and you can see the points here are the elements. So this is a straight line between here, here, and here. Actually, let me stick in a straight line just for clarity. So just to convince you, this is the same bit of code you've just seen. And then what I'm going to do is I'm going to stick in, let's have a straight line between the elements there. So you can see with 3 elements, it's a fairly poor approximation of that parabolic. But essentially we have something that is at least correct at those various points. Okay, so now let's talk about a non-zero boundary condition. So let's take the example we looked at last week. In this example we're going to set f is equal to 0, so we actually go back to the equation we had last week, where this is just equal to 0 on this right hand side. And we're specifying the boundary condition at x equals 0, and we're going to specify at t equals 60 at 0.3. So if you remember, the solution of this was a straight line, basically going between up to 60 here at 0.3. So this is the exact solution, and we essentially want to enforce that boundary condition in our system. So a non-zero boundary condition requires a little bit of thought. So as we've seen for the zero boundary condition, in this case, we just look at this and say, well, okay, each of these terms is going to be multiplied by 0, so let's get rid of that column, let's get rid of the corresponding row. That enforces the zero boundary condition. For non-zero boundary conditions, the way to understand these is to consider 3 simultaneous equations. So what I want you to do here is just take those simultaneous equations and say someone told you that the value of z is equal to 2. What would you do to solve these equations? So the first thing I want you to do is actually just to go through and form a matrix from this entire set of equations. So I want you to basically put all the coefficients, as we did at the beginning of last week, into a matrix x, y, and z is equal to the right hand side. So start by doing that for the entire set of systems. Then substituting a known value of z and repeat that process of forming a matrix again for the system, given the fact you know that z is equal to 2. Does that make sense? So the idea here is, well, no. So the point is, once you've added z in, there's one fewer unknown here. So what you're going to end up having is a matrix that's reduced, but in terms of x and y. So do it first of all for the entire system, including z. Then put in the fact that you know the value of z, substituting 2 for each value of z, and then reform a matrix just in terms of x and y. And any questions again, please let me know. Any questions about this? Anyone notice anything? Seem okay or? Okay, let me go through this because we've got 15 minutes left. So, with this example, the first part is trivial. We just stick in the values of the coefficients. So this is just 1, 1, and then 0 for the first row. For the second, we have 2, minus 4, and then 1. And that's equal to 1, 0. And in this case, it's just 1, minus 2, 3. Is equal to 2. Now for the second part, the first process of sticking the values of z in is fairly straightforward. So for 2 and 3 equations, we get 2x minus 4y plus 2 is equal to 0. And then we can just move that over to the left hand side, so that's just equal to minus 2. And we have x minus 2y is equal to, plus 6 is equal to 2, and again we can just move this over to the right hand side, and that gives us minus 4. Does that make sense? Does everyone agree with that? But then you've actually got 3 equations and only 2 unknowns now. So in matrix form, we can write this as 1, 1, and then maybe have this equation 2, minus 4, and minus 2. But we could equally have written this equation here. For 1, minus 2, and minus 4. So, in this particular case, by substituting that in, we essentially have too many equations for unknowns. Now, one of the things about finite element process is you are essentially constructing the system that you want to solve. So this is why you're actually eliminating that bottom row, essentially, because in doing that, you're essentially taking out the bottom row and the column to make sure you've always got a system of matrices that you can actually solve. More generally, for this process, essentially what we're doing here is we're solving for a system of equations where just basically each coefficient is just denoted by A11, A12, and so on, just to kind of keep track of where it would be in the matrix. We essentially would form a matrix like this, that's A11, A12 for each position. It's equal to 0, and you can see that essentially for a known value of Z1, what happens is we basically take the coefficient of 1, 3 multiplied by z1 and move it to the right hand side. Similarly for a 2, 3, multiply it by z and move it to the right hand side. So if you actually look at what you did here, we essentially substituted in the known value for z here, and then we moved it to the right hand side. So the process is always that. We actually substitute in the value we know, and we move that to the right hand side of the top equations. So as a general process, that's essentially how we apply boundary conditions for one dimensions. So you can see here, and this ambiguity is removed in the finite element process by just taking out essentially the bottom row, or the last value that's a function of z there. We very clearly have two equations left over, and then it's always just this coefficient moved over, multiplied by the value we know, and so on. So to show you, for say, an example for a set of simultaneous equations that we would get for the finite element process, so this is just an equation for three elements, 1, 2 and 3. You can see essentially what we do is we cancel out that set of equations, and then we move minus t4 divided by h over to the right hand side. We end up with a system of equations where we have just a reduced matrix with that bottom boundary condition enforced there. So this is what you saw in the notes at the end of last week when they actually enforced that bottom boundary condition. It's essentially just a process of rearranging. So hopefully that makes sense, but it's essentially, if you work through the simultaneous equations and you see what you're doing is substituting in a value, rearranging to get the value you know on the right hand side, and then just cancelling out that bottom equation, because that bottom equation is already over-defined in your system by the fact you know or want to specify T4. Okay, so this example here shows you in Matlab code. It's identical to the one you've just seen, other than the following. You've got this here, use red. So this here, the bottom boundary condition we have here. There's no forcing term in this example. Sorry, this is a mistake here. This should be 0, and this should be, so T4 in our case is 60 divided by 0.1, so 600. For this particular example there. And then otherwise it's exactly the same process. You form up the matrix of k values that's identical to previous, and then you just essentially solve for the solution. And let me just show you that for Matlab code. And you can see here we're comparing to the linear example for correct flow that we derived last week. So you can see we essentially get a straight line between 0 and 60. And the circles are the nodes where the finite elements connect up. Okay, so the last thing I want to show you just from the Matlab code, and again these are all on Blackboard, so I encourage you to play around with these, is an example which is kind of a general element example. So it's exactly the same process again. We define the elements, we define a number of elements, we define both boundary condition, top and bottom boundary here are just defined as TB and T bottom and T top. And in the process, instead of just inverting a matrix as we did before, so if you look at the slides here, what I've done is define K explicitly just as a matrix in one line. What we're doing now instead is we're looping in the way I talked about in that first set of slides, basically looping over each of the elements, and then for each of the nodes for those elements, what we're doing is we're building up a K matrix. Now, if you look at the form of that K matrix, the diagonals are almost always minus 2 over H. And the off diagonals are always 1 over H. So the process of that is essentially to loop through I and J for the nodes of each element and build up this K matrix. So it's a kind of general way of building up a global matrix. And then we specify the boundary conditions. So in our particular case, we're specifying that the F1 and F nodes at the top and bottom boundary condition are equal to those values. And then we're essentially going through and doing this process of taking away from the right hand side the top and bottom boundary conditions. So it's essentially the process you've just seen. Firstly, on the right hand side, we're saying force times H, if we have a force, top boundary condition, bottom boundary condition. And then this process here is basically setting each of the other K elements to be equal to 0. So that's cancelling the rows of the matrix. Let me just show you up till now what that does. So what's nice in Matlab is you can actually highlight code and press F9 and it runs it. And then you can actually look at the values that you get from that. So let me just run that. And then what we can actually look at is the K matrix here. And you can see the K matrix here has actually got the values for K of minus 20 and 10 that we saw in that example. And then everything else has been set to 0, other than this kind of 1 on the diagonal. So this is just a kind of a generalization of the process you've seen. Now what's quite nice is then you can increase the number of elements, because we've got it in a general form, say to 8. We run the example we've just seen, And it should, maybe it's already plotted. And you can see it's plotted, oh, 1 second, sorry. So it's plotted over the top of the last one. So we run that again. And you can see we get a straight line, but with more elements. Now, because the straight line's already an exact solution, that's not particularly interesting. But if you remember before, that parabolic profile, which we had, was a fairly poor approximation. Let's say we put in a force of 1 and a 0 boundary condition here. And we run that again. You can see with 8 elements, we've actually got a much better approximation. And so you can keep increasing the number of elements, and you'll get a kind of closer and closer approximation to the correct solution of a parabolic profile. So please feel free to play with that, get an idea of how that works, especially if you've not used Matlab before, because this is kind of the essential understanding that you'll need in order to do the next part. Okay, so we've got we've got about 5 minutes left. So I just want to finish by talking about the final example here, which is basically another extension to that underlying equation. Now, the notes online cover this, so for next lecture I'd like you to go through, work through and understand this. The process for this term you already know. It's exactly the same as what you've seen, we've gone through for the last 2 lectures. It's this term that's going to be different. So first of all, solving this exactly, which we talked about in the first lecture, is one of essentially going through and solving using some textbook solution on second order homogeneous linear differential equations with constant coefficients, which is a bit of a mouthful, but essentially just you form an equation for the coefficients and you find the solutions of the form of a cosine and a sine. So what this means is it's an underlying function that we can't approximate exactly. Sine and cosine are transcendental functions, which means no amount of straight lines would ever approximate them exactly. So we're always going to be an approximate solution, which is nice because we can actually then look at how close we can get as we increase the accuracy. But it goes through step by step. The reason this is interesting is we're looking at this example, we now have this term and this term. So we're kind of building the complexity towards the example in the exercise. So the process here is one of how do you solve this term. In order to do that, we essentially use the same trick we used before of sticking in the shape functions. What you'll notice in doing this is that we end up with the product of 2 shape functions, which is going to be omega 1 n1 plus omega 2 n2 times t1 n1 plus t2 n2. When you multiply these out, you're going to get omega 1 t1 n squared plus omega 1 t2 n1 n2 plus omega 2 t1 n2 n1 again plus omega 2 t2 n squared 2 squared. So the reason, so this should be 1. So the reason I've written this out is because it's essentially we've now got terms which are squared in terms of n, and actually approaching those directly using the shape functions we've seen already ends up being quite complicated. Now feel free to work through the mathematics on that directly if you want, but essentially there's a better way of working, and this is using what are called shape functions or local coordinate systems. So this comes back to your question about local and global systems. Remember before, because we're having to specify each one as U1, U2 each time, we had to write a separate bit of code for each of them. What's more convenient is to actually work so that each element function itself is always in a coordinate system that goes between -1 and +1. So the process of that is essentially deriving exactly the same thing we've done before, where we derive a straight line, mx plus c, where we're using, in this case, psi, and we do exactly the same process of taking 2 simultaneous equations where the 2 boundary conditions psi are -1 and +1 for the values u1 and u2. And if you work through the mathematics on that, you end up with an expression. Well, let me just show you very quickly this, and then this will be the last thing. So we can add together the 2 expressions, and that gives us u1 plus u2 is equal to 2 times c, which means c is just equal to u1 plus u2 over 2, and we can do let's do 2 minus u1, and that just gives us u2 minus u1 is equal to 2 times m. So we have m is equal to u2 minus u1 over 2 as well. So what we end up with is an expression for an equation for mx plus c of u as a function of x is equal to u2 minus u1 over 2 times psi plus u1 plus u2 over 2. and then essentially we assemble that of the form u element is equal to 1 minus psi over 2 u1 plus 1 plus psi over 2 u2. And then you can do all of the same tricks. So you can take derivatives of this u epsilon by u psi, and in working in this particular system, a number of things become easier. So the process you'll go through when you work through these notes is one of essentially using these shape functions. It's like a substitution. When you come to complex integration, you essentially use a substitution to make the system easier to solve. These shape functions are a way of doing that. So this was explained in the first set of notes, these shape functions, but they're also covered again in the latest set of notes. Everything you see in here is just algebra. There's nothing more complex. All of the concepts that you've seen already are the same. The integration by parts, substituting of shape functions, work through the mathematics, collect returns in omega, form a matrix. So please go through. Any questions at all, feel free to ask me, feel free to email, put them on Blackboard. And the online survey will be open all week, so please feel free to comment on this. I didn't understand this, please spend more time on this, cover this again, whatever you want to cover, please stick it on there.